Sairam, everybody. We welcome you all to the final and concluding session of the International Online Symposium on Recent Advances in Chemical Sciences. Now, I request Dr. Rajiv Nair to introduce the next speaker.
Our next speaker is Dr. Shamraja, Associate Vice President, Technology and Engineering at Raj Industries Limited, Pune. He had his Masters in Life Science with specialization in Environmental Biology from Sri Sathya Sai Institute of Higher Learning and PhD in Environmental Science and Engineering from IIT Mumbai. He has more than 25 years of engineering and construction experience in the field of water and wastewater treatment. He has worked across all relevant departments of wastewater business, which includes process design, R&D, and project management. He has expertise and knowledge based in advanced wastewater treatment processes and has designed and executed wastewater recycle plants for industrial clients. He has worked with many reputed MNCs in India as well as the Middle East marketers like Reliance India Limited, Hindustan Petroleum, ITC, etc. With all this brief introduction, I would like to welcome Dr. Shamraja for his presentation. Welcome, sir.
Sairam and pranams to everyone, and I would like to make this presentation as a humble offering at the lotus feet of my loving Lord. I would like to thank the entire chemistry department for having given me this opportunity to make a presentation on a subject that has been probably a little slightly different from what you have been hearing for the last 1.5 days. So when Professor Sundaresan asked me to speak something on water and wastewater, and he told me that the symposium is on advances in chemical sciences. I was wondering whether this is the subject that would interest some of the budding research scholars in the institute. But I think water is one of the most important part of our life, and without water, we cannot obviously survive. So I would like to once again extend my thanks to the entire team for this opportunity, and I will try to make it as short and as interesting as possible. I'm sure you all have had a good lunch, and being a Sunday afternoon, most of us want to relax on a Sunday afternoon so that we are ready for the next day. Nevertheless, I will walk you through this presentation on water and wastewater, where I will first handle the water treatment plan, which is the drinking water, and then I will take you through what is wastewater treatment. So basically, it will be an overview, and if you have any questions, you can note it down and ask me at the end of the session. I'll also briefly introduce my company where I'm working. I'm currently the Associate Vice President and heading the Technology and Process Engineering department of the Water and Wastewater unit of my company. The company is almost 37 years old, and we have our presence in 750. We have 750 references and presence in more than 75 countries all over the world. So predominantly, Praj industry is into bioenergy. Basically, we are the leaders in distilleries and breweries. And most of the distilleries and breweries in the country, like more than 70-75%, has been set up by Praj Industries. And we have 5 verticals, the main being bioenergy, which is categorized as 1G, that is bioethanol. And the other one is 2G, which is called as the ethanol for blending with oil, that is basically your diesel or petrol, which is gaining more and more importance now with this fossil fuel being exhausted. The other division we have is high purity, where we manufacture and we produce very high purity water, especially for the pharma and cosmetic industries, where they require very sterile water for their formulations. And we also have a very big fabrication unit, wherein we do fabrication of large equipments, very large equipments, and we supply it to many of these contractors like L&T and other big companies who are into engineering projects. And one of the main vertical where I am associated is water, wastewater, where we give complete water treatment as well as wastewater treatment solution as a turnkey contractor. We design, engineer, supply, and erect and also commission the plant. We also do operation and maintenance of these plants. And we are one of the very few companies in India who can offer the complete end-to-end solutions in water and wastewater, including what is called as ZLD, that is zero liquid discharge, which is becoming more and more relevant today because the Pollution Control Board is tightening their nose in all these industries where they have been uh, releasing all the water outside the premises and polluting the environment around. So now they have been asked to put up a ZLD plant where not a single drop of water can go out and pollute the environment, and you have to recycle and reuse all the wastewater that is generated. We also have a very big, this is our basic R&D, which is called as Matrix. It's a 100 crore investment. We do a lot of research. We have almost 100 scientists, all of them PhDs, and also a lot of postgraduates who are working on many of the solutions that we offer to our customers. And it includes the development of new products which is more environment friendly and green chemicals. And we also have a facility where we can do piloting of the products that we are doing a lot of research and giving to the chemical industries predominantly. So we have a very large facility where do all the piloting, and then it is scaled up to the field scale units. Coming to the main topic on water, we all know water, the elixir of life, Amrit, what all, it has been given all the important names because without water we don't exist. It's a very precious resource, and as you can see, the distribution of water on Earth's surface is very, very uneven, extremely uneven. Only 3% of water on the surface is actually fresh. The remaining 97% is ocean. Out of the fresh water, 69% resides in the glaciers, all as ice, 30% as underground, and less than 1% in lakes and rivers, which is the main source of water for all of us, not only human beings, but even the other living beings. So if you see 1% of water on Earth's surface is usable by all the living beings on Earth, including 7.8 billion human beings as of today. It's going to increase more. And 99% of this is unusable. So we can understand it's not a finite source, it's not an infinite source, it's a finite source. And therefore, for future sustenance, it is imminent that we need to reduce the consumption of water as much as possible. We need to conserve it. Not only that, we have to also reduce, recycle, and reuse as much water as possible. The main use of water that is available for human beings are basically can be categorized as domestic and industrial use. And domestic use, most of the usage is for drinking, cooking, washing, gardening, and all the bathrooms washings. Whereas the industrial use, you have boiler feed water, then you have demineralized water. And as I told you earlier, high purity, that is your pharma and food waste. And of course, a lot of these industries like textiles, tanneries, pulp and paper consume a lot of water to produce one unit of the product. And so you can see how the water consumption is only increasing day by day with both industrialization as well as the increase in population. It may seem very simple, but water is one of the most it's one of the most trickiest chemistry. So there lies your chemistry in this. Water chemistry is very intriguing. It's very difficult to understand, though it looks very simple. So when you have the main source of water, that is the source of drinking water, which are the streams, the lakes, rivers, and aquifers, which is your groundwater. And then we are looking more and more onto the oceans because the freshwater source is limited. So now we have more and more people putting up the desalination plants where seawater is converted to drinking water. This is more predominant in the Middle East, where there is absolutely no source of fresh water. They have to depend on the seawater, and the seawater is converted into drinking water. Let's look at some of the natural contaminants in the drinking water source that we have. So if you look at the surface water, that is the rivers and lakes, predominantly it contains suspended solids and colloidal matter. So most of the time you find that these resources are highly turbid, and you can see a lot of suspensions in this water. It also contains a lot of dissolved iron, because iron is one of the most common elements on this Earth's crust. And besides, some of the sources also have color and some sort of a taste, mild taste. And there are also resources where there are runoff, which is called as the agricultural runoff, like pesticides and other things, which also contaminate the surface water that is available. And of course, pathogens like bacteria, virus, and to a certain extent, algae, depends on what is the source and where the source lies. As far as the groundwater is concerned, predominantly it is all dissolved. You have very less suspended solids, because by the time it reaches to the bottom of the aquifer, it is already filtered through the layers of sand and then rocks. And then by the time it comes down, the suspended solids are filtered naturally. However, it picks up a lot of the elements that are there, like the fluorides, arsenic, nitrates, iron, and a lot of dissolved salts. But if you see most of the cases, it is hardness. It is calcium and magnesium which causes hardness of the water. So typically in Puttaparthi also, if you see, we have been using the groundwater as the main source of drinking and all other activities. It is slightly hard. It is not a very soft water. When you drink, you can find that it is little hard. It is very difficult to form the soap. And then the final source is seawater. If we don't get surface water adequately, we have to look into the seawater as a source. So the main contaminants in seawater are the zooplanktons, which are floating matter predominantly. And then you have algal blooms that come in suddenly, and you have all these red algae and green algae taking vast expanse of the seawater. And of course, predominantly dissolved salt, that is sodium chloride. So it's normally around 3 to 4.5%, depending on which side of the globe the ocean lies. I'll take you through a pictorial tour of how the drinking water treatment is done. So if you see this, most of the drinking water that is the surface source, be it river, streams, are very turbid. We can see that this is a raw wastewater, raw water, and this water has to be converted to drinking water, which has to be odorless, colorless, soft, and it should be free from any suspended solid. So it should be as clear as this. And that's why nowadays we are taking a lot of bottled water, which is actually highly treated before it is bottled. There are drinking standards that has been set up by every government. As far as Indian government is concerned, there is an IS standard, which is called as IS 10500, where you can see the most of the parameters which are most important for drinking is color. Up to 5 Hazen units is what is permitted. Then you have odor. It should be agreeable. Most of us wouldn't like to drink water which has got slight odor. The pH should be in the range of 6.5 to 8.5. And the taste also should be agreeable, in the sense that sometimes the water tastes very bad and we are not able to drink the water. The turbidity has to be less than 1 NTU, that is nephelometric unit. And dissolved solids, though what is desired is less than 200, which is normally the soft water or sweet water, what we call. But up to 500, you can still make it drinkable. The maximum limit is around 2000 milligrams per liter. So these are all milligrams per liter. So what are the objectives, the primary objectives of water treatment for drinking? First and foremost thing that we need to attack is the particulate matter, which is the colloidal or the muddy constituent of the water. And to remove these particulates, we use a lot of chemistry in terms of for actually settling this matter. So if you naturally keep the water for some time in a container, the solids, the suspended solids, gradually settle down. Then you get a fairly clear water at the top, which can be decanted and used for drinking. Still, it will have colloidal matter, which is not desirable to consume. Hence, there are different steps in the water treatment plan where you actually target different constituents, which I had mentioned earlier. So the first one, as I told you, is removal of particulates, where you add coagulants. Essentially, it is iron or aluminium-based coagulants. These are alum or ferric chloride, which is used. And these coagulants basically break the charges. All the colloids are normally negatively charged. When you add these metal coagulants, which are positively charged, they neutralize the charge on the colloids. And then they start forming, since they don't otherwise settle because the density is very low. Coagulation helps in discharging these charges on the colloid matter, and they come together. Now, when they come together, they start forming larger particles and the density increases slowly. To aid this density increase, we add something what is called as a flocculant. So generally for drinking water, these are high purity flocculants, and because these are synthetic chemicals and it is not desirable, but still sometimes flocculants are added. It's called as a polyelectrolyte, and then it increases the weight or the density of these particles and it settles very fast. So you have the first step of solid separations from the water, and that is your settling tanks. And further, the colloidal matter which doesn't settle goes through a filtration unit, which we call as a rapid gravity filter or sand filter. Essentially, sand is the media. And then it can also be taken through membranes. The latest technologies are when you provide these ultrafiltration membranes, where it can take off almost 99.9% of the colloidal matter. And what comes out, the permeate is absolutely clear. And you can drink the water directly, of course, after disinfection. Now, some of the water source, since it contains hardness, like especially the groundwater, if it is used for drinking, we need to take out the hardness, that is the calcium and magnesium hardness. So if you have you have permanent and also temporary hardness. So temporary hardness can be removed by simply boiling the water. All the calcium and magnesium carbonates, they just precipitate. However, for permanent hardness, which is predominantly chloride and sulfates of calcium and magnesium, you need to precipitate this by using lime soda softening. Now, once the dissolved salts are precipitated, then there are certain components, like as I told you, there might be some residual pesticides, which you need to completely take it out from the water, for which we use adsorption, which is predominantly carbon adsorption, activated carbon. And then sometimes there are some volatile components in the water, which is not very common, but sometimes it is there, and then you can use air stripping. Now, if the pesticides they persist in the drinking water, you can use an oxidation process where you oxidize the pesticide and further treat it through another set of carbon filters and get it absorbed. And finally, the pathogens, that is bacteria and virus, which is also very, very important to the remove. You need to disinfect it, and for disinfection, we use predominantly chlorination, because chlorine has a very high life as they form chloramines, and the presence of chloramines actually prevent reintroduction of the bacteria into the water. So most of the water after treatment is stored in large tanks or in reservoirs, where it is further distributed down to the population or at the end of use. So hence, it has to be ensured that there is no recontamination of bacteria. And that's why chlorine is predominantly used. However, we can still use UV radiation and also ozonation as the disinfection agent. So this is a flow sheet, a very common flow sheet for drinking water treatment. So you have the source, that is the lake, and there's an intake pipe from where it goes through a preliminary screening, because many of these sources are open. So you have a lot of floating, especially if it is near the vegetation, you have a lot of floating matter like leaves and other things which come. So you just have a very, very crude type of a treatment where you remove the floating matter, either manually, which is okay for a very small capacity, but for very large capacities, most of the municipal corporations have in million liters per day. The capacity is mentioned as 100 million, 200 million, 500 million. So these are all very huge water treatment plants. So obviously you require mechanisms. So you have mechanical screens. We also call it a traveling screen. And then it comes to a lift station where it has to be pumped to the water treatment area. And so we provide a lot of pumps depending on the capacity of the water. That is the output capacity of the water. And the water, drinking water, the raw water is pumped into a coagulation or a settling tank, before which the chemicals are added. The chemical coagulants are added. You also have a pre-chlorination step initially, because there are certain dissolved iron which is in the form of Fe2 plus, and you need to convert into Fe3 plus, which actually comes out as particulate matter, and it can be settled downstream in the flocculation or the settling tank. So the chemical is added into this flocculation tank where your coagulation and flocculation process takes place. It's roughly around half an hour you give time for the chemicals to react. And then it is taken into a sedimentation basin. It's basically a settler, so you have huge tanks which is either circular or rectangular in shape. And then you have a mechanical system to remove the sludge that is settled at the bottom of this tank. So you have the sedimentation where you have a slope at the bottom, and then all the settled sludge can be removed from here, from this bottom of the tank, and the clear water overflows. So this is, you must remember, this is a continuous process. So this pumping and this entire thing is going on 24/7, 365 days, except for some days when it is taken out for maintenance. Still, every system is given a standby so that there is no time where the water treatment is not operational. So further, after the segmentation basin, as I told you, there are some colloidal matter still remaining in the overflow of the settling tank. So it's taken into a rapid gravity sand filter, where you can see that the bottom is of gravel. You have the support structure as a gravel, and then you have sand on top, and then anthracite. Anthracite is diatomaceous earth, so it has some absorption capacities. So some of the obnoxious dissolved matter is absorbed onto anthracite, and then the colloids are filtered through this, and the filtered water is then taken into a post-chlorination tank where you need to disinfect to remove the bacteria and viruses. So we add around 1 to 2 milligram per liter of chlorine, which is sufficient enough to take care of the bacteria and virus, to kill most of them. And then during the distribution stage, before the distribution, after this treatment, it goes again into a reservoir, and from the reservoir it is pumped into overhead tanks, and the water distribution is done through the overhead tanks. Now the residual chlorine which is there takes care of the prevention of recontamination of bacteria and virus back into the drinking water. So this is an overall scheme of how a normal drinking water is treated in a municipal level treatment unit. So if it is a groundwater, as I told you, you need to take out the dissolved matter like hardness, and then again disinfect, because again we have a reservoir downstream before it is used for consumption. So these are some of the units, the actual units that are given in a water treatment plant. What you see here is a cascade aerator. It looks like a very beautiful fountain, but actually what is done is the raw water contains iron in the form of Fe2 plus, and when you aerate it naturally, the oxygen diffuses into the water, and it oxidizes the Fe2 plus into Fe3 plus, which is particulate in matter, and the iron particle settles on these steps. So basically, you are removing the iron, you're converting the dissolved iron into particulate iron, and then taking it out before it goes into the sedimentation tank or the clarifiers. So on the right side, you see the sedimentation tank. The sedimentation tank, or what we call as clarifiers, are generally circular in structure. So these are the mechanisms. So water after the cascade aeration comes here, and before entering the sedimentation tank, you have the flocculation and coagulation of the particulate matter. So here it comes and it settles, and what you see here is a clear water. This is a clear water, just overflows and comes into rapid sand gravity filters. So these are large filter houses. This is the filter house, and are you able to see my cursor? I hope so. Anyway, so these are the filter houses, and these are the series of filters, and the water is filtered through this sand filter, and the filtrate is collected at the bottom, and from the bottom is taken into a chlorination unit where you have generally for a very large plants you have gas chlorination. So you have these gas cylinders which is full of chlorine gas, and chlorine is taken out. We have a separate chlorination unit from where the chlorine from the gas is taken into this smaller unit, and it is dosed into the water. So that ends the treatment part as far as the drinking water is concerned. Now for groundwater, as I told you earlier, hardness can be removed by boiling. It can also be removed by resin bed, which is essentially what we call as a soft bed. So they are ion exchange resin beds, and they exchange the calcium and magnesium. And for the permanent type of hardness, we need to go in for a lime soda softening, where the calcium and magnesium is precipitated out. There are cases, in fact, many cases where the groundwater is contaminated with arsenic, which is very poisonous. Then you have iron, and you also have fluoride, which is one of the main contaminants. And we are quite well aware of the problems of fluoride in Puttaparthi itself and many of the places in Andhra Pradesh. Fluoride is a big concern as it causes fluorosis and other complications. And these components can be removed by chemical precipitation, by filtration, by adsorption, and by ion exchange resin beds, and also membrane processes, which is the reverse osmosis. So RO is one of the most sophisticated technologies for removing most of the dissolved components, including the monovalent like sodium and chloride. And the dissolved solids, like for example, C, you have to go in for softening, and then ultrafiltration and RO. Ultrafiltration is nothing but membrane-based system where you have membranes of 0.04 microns. So it filters all the particles above 0.04 microns, and it protects the downstream reverse osmosis membrane, which is a very expensive equipment in the whole water treatment plant. So this is just a flow sheet of how an industrial water treatment plant looks like. As I told you, industrial water requires very high purity water depending on the point of use. So in industrial water treatment, you have typically the source. Either there are corporations like, for example, MIDC, which is Maharashtra Industrial Development Corporation. They have their own water treatment plants. And these treatment plants are specifically for the use of the industries. So they supply the water to these industries. And if there is no surface water source, the groundwater becomes the main source of water. And then it goes through a series of treatment processes, like the main process may require a very high purity water. So you have certain treatment given for the processed water quality. Then you have demineralized plant, that is DM water. Again, it's an ultra pure water. You have to take it through a series of beds, anion cation exchange bed, and then you have mixed bed, and then further it is taken into the what you call the end use, where again they require very low percentage of cations and anions. Then for the pharma applications, as I told you earlier, you require sterile water and high purity water, which again is a separate treatment technology altogether. So water treatment per se, depending on the end use, have either a simple treatment like we do for drinking water application, and very complicated basically for the industrial use. So the cost of water treatment is dependent on the final quality that you require of the treated water. Now, more and more corporations, more and as the organization is increasing, the cities, the populations in the city is increasing. There is very little water available, and all these cities which are near to the sea are looking at seawater as the main source of drinking water. And this is predominantly true in most of the Middle East countries where there is absolutely no source of surface water available. And even if you have gone through the news a couple of weeks back, even in the USA, in California, they are water starved, and water has become a commodity for trading. So you can understand the future that we are going into if you don't have the source of water. And seawater is extremely expensive to be treated because it has to go through all the sophisticated technologies like the UF, the RO, and at the end of it, there is a byproduct which is highly concentrated and it is full of salt. How do you dispose the salt? That itself is a big problem. It's a big challenge. So things are not that easy. At the same time, if we are able to recycle and reuse most of the water, that is going to be our solution. So if you look at the average daily water consumption usage per person in the world, USA has the highest per capita consumption, as high as 600 liters per day per person. And then the European countries. So the water consumption in all these highly developed countries are very, very high. And I would say most of them are actually wasting their water, which is a very valuable resource. And if you see the graph, as the countries have become less and less developed, the water consumption also reduces, predominantly because it's not very cheap to buy water, treated water. And as the water consumption reduces, it means that all these countries who are getting less and less water, either because the source is limited, or their water treatment facilities are limited, or they are in a water starved area and water stressed area. And India is one of the water stressed area, and it has been said that in future India is going to go through a very difficult time in satisfying the water needs of majority of its population. So it is very important for us to understand how water has to be conserved and used as little as possible so that we conserve this water for our future generations. So the unless you use water, there is no wastewater generated, right? So wastewater is nothing but the water that is used and wasted either by human activity or by industrial activities. So essentially, it means you are using the highly treated water, you contaminate it by all your different types of uses, and then this contaminated water is just disposed, and it's left to generally it is left to the nature to take care of it. Of course, nature takes care of it, but to a certain limit. It cannot go on doing this forever unless we intervene and we take responsibility for the waste that we generate. So I will now come into wastewater treatment, which is very important. I think it's the most important subject for all of us to understand, because we are all equally responsible for the amount of waste that is generated in the country and all over the world, in fact, the entire human population. 80% of the water that we consume, drinking water, 80% of the water we consume is converted to wastewater. And it predominantly comes from our bathrooms and toilets. And the source in a domestic wastewater is kitchen, washrooms, wash basins, and laundry. So you imagine you take 100 liters of water, only 20% is used for your normal consumption of cooking. And then 80% is what is a wastewater that you generate. So if you calculate per capita generation, you can imagine what will be the amount of wastewater that is generated. It runs into millions and millions. So I would again come back to the first slide, which I showed you about the state of water, the availability of water, where I said it's not an infinite source. It is a finite source. And we need to really be very serious in conserving water at source and minimizing the wastewater. And even if because you cannot eliminate wastewater is going to be there. But how do you manage the wastewater? So it is best that we go and follow the principle of 3R, that is reduce, recycle, and reuse. There is no other option that is left. So as the population is growing, and there is a lot of economic shift towards more resource exploitation. Intensive consumption patterns have been found for the global freshwater use. And the freshwater withdrawals for agriculture, industry, municipal uses, etc., has increased almost sixfold since the 1900s. Now, the chart shows that the rate at which the global freshwater use has increased from 1950 is alarming. But if you see there is a small drop, there's a small hope that the consumption is reducing. Only that is also towards the after 2000, because a lot of thrust has been put on recycle and reuse. And today, not only the industries, the municipal corporations also are very conscious about the fact that water needs to be conserved, water needs to be protected for the future generation, for the sustenance of this earth itself. And so we come to the topic of how to treat this wastewater, the domestic wastewater. I'm not going to touch on the industrial wastewater because it's a very vast subject, and the more the usage, the more complicated the wastewater becomes in terms of its components, its constituents, etc. So if you classify the domestic wastewater in terms of the generation, the majority, you have two classification. One is called as the black water and the other is the gray water. So black water is the urine and feces which is generated through the toilets, through usage of the toilets. Whereas the gray water is predominantly from the washing, your laundries, your bathing and kitchen. So you can segregate these two and recycle separately, or you can mix these together and then treat it together as a single domestic wastewater. It all depends on the place where you need to, and ultimately the treated water quality that you require for where you are to go to, you're going to use the treated wastewater. Now, the typical consumption, the composition of sewage, domestic wastewater. The contaminants are predominantly suspended solids, which we have seen is also a part of the drinking water treatment. But this suspended solids is different from the suspended solids that you have seen in the drinking water. You also have the dissolved organics, which is classified or termed as BOD and COD. BOD is biological oxygen demand, and COD is chemical oxygen demand. Both are essentially the same, only thing depending on the analysis and the constituent it is segregated. So it's very difficult to individually know what is the contaminant. Like I cannot keep on analyzing each and every component in the wastewater. So best is you take a parameter which defines the amount of contaminant, the what you call the scale of contaminants. And so when the biological oxygen demand or the BOD concept has come, where we know that when these water is without treatment, if you leave it to any water body, either lakes or rivers, there is a biological oxygen that it demands to naturally degrade these organics. So that is called as the biological oxygen demand. So there is an analysis which gives you how much is the BOD. And it's normally in the range of 180 to 350 milligram per liter. And chemical oxygen demand includes the BOD, but it also includes the organics which are non-biodegradable. So always the COD will be higher than the BOD. As you see, it is around 400 to 500 milligrams per liter. And then we have ammonia, which is all your amino acids, your proteins, what you eat, your digestion and your products. Byproducts of your digestion is predominantly nitrogen and phosphorus. So your sewage will contain ammonia, nitrogen, and organic nitrogen, and also phosphorus. And then the most important is your pathogens, your fecal coliforms and MPN, what we call as the MPN. So these are all indicators of the level of contaminants in a domestic wastewater. In a sewage treatment plant, there is a typical flow sheet where, depending on the constituents that you need to separate or treat, there is a flow sheet that has been developed, which is a very conventional flow sheet. So most of the sewage that is generated from the household, these are collected through drain pipes and it goes into, earlier there used to be septic tanks, but septic tanks also has become a problem because the overflow from the septic tank ultimately goes into your groundwater and contaminates the groundwater. So in large cities and municipal corporations, you have a sewerage connection system where the sewage from all these households are collected and conveyed through pipelines through to a centralized sewage treatment plant units, where all the contaminants of the sewage is treated stage-wise. So when there is a conveyance, if the conveyance is, even if it is through a pipeline or an open drain, which is normally not there. Nowadays, open drains are not permitted. It is generally through underground pipes. It contains a lot of floating matter because people just push in everything into the toilet. And when it comes to the end of the pipe, where it comes into the sewage treatment plant, you will find all sorts of things that are irresponsibly put by people into the toilets. They just flush it through the toilet. So it contains a lot of floating matters which needs to be removed. So then you have what you call as the screening, bar screening, where there are a lot of mechanical screens which traps all the floating matters. And downstream, the water goes minus all these floating matters. The floating matters are screened, and there are raking mechanisms where it is taken out and then separately mixed with the solid waste management and dumped. Now, after that screening is done, it still contains a lot of heavy particles having specific gravity of more than 2.5, which is predominantly sand and other things which it picks up on the way. And that also has to be separated. So we give something called as a grit removal system or a grit separator. Or the grit separator is again a settling tank, because anything beyond 2.5 settles very fast. So all the grit is separated, and whatever particulate matters are mixed along with the top layer of the settling tank, it goes into what we call as a primary clarifier. Again, it's a settling tank where you can add chemicals and settle the colloidal matter. So it's basically a solid liquid separation equipment. And once the insoluble particulate matters are removed, what remains in the sewage is predominantly dissolved organics in the form of BOD and COD, which I mentioned earlier, which has to be removed by a biological system. Biological, here we use chemistry, we have to use microbiology, we have to use everything. So it's basically an interdisciplinary field. And so you need to have a good knowledge about the micro organisms, how the bacteria actually functions. And so what is done, which actually occurs naturally, is basically put into a mechanized unit, what we call as an aeration tank. We give oxygen as a source because the bacteria uses the organics as its food source, converts it into water vapor and also energy. It gets energy, and part of it is converted into new biomass. For that, we require oxygen. Oxygen is supplied through air blower system. We have a diffuser system. I'll show you some of the photographs which will show you actually how the plant looks like. So what happens is the bacteria converts the dissolved organics into water vapor, and that is actually what is getting treated. So at the end of the aeration tank, you have the biomass, that is the excess biomass that is generated, the bacterial biomass, which needs to be separated again, because you need to have a clear water at the end of the treatment plant. So what goes into the settling tank is nothing but treated water along with the excess biomass. These biomass is settled in the clarifier. This is called as a secondary clarifier. And from there, the sludge is taken out from the bottom for further treatment for sludge digestion and other things, which I will talk about in a few minutes from now. And the clear water, again, has to be chlorinated because it is predominantly fecal coliforms and other pathogens. It is not rid of most of the pathogens. So you have to chlorinate it. And after chlorination, if it has to be discharged to any receiving water body, then it can be discharged, where the levels of BOD and COD has been fixed by the Pollution Control Board. It suspended solid concentration cannot exceed more than 30 milligrams per liter. Your BOD, total BOD, has to be around 30 milligrams per liter. And actually, the nitrogen and phosphorus also need to be very low. But somehow in India, yet the nutrient removal has not been given so much of importance. But if you don't remove the nutrients, the nitrogen and phosphorus, is going to cause eutrophication of all the water bodies where this treated sewage is, ultimately going. So the fundamental principle is that after treatment in a sewage treatment plant, all these treated water will get diluted further, either in the receiving water body like a river or a lake or any other water body where there is some source of fresh water also coming in. So as I told you, I'll just run through the flow sheet. This is a pre-treatment, and you can see there is a screen, a mechanical screen, where continuously it removes the floating matter from the sewage, and the floating matter is separated from the water. And then it comes into a grit chamber. So the grit chamber is basically, again, a sedimentation tank. And in the sedimentation tank, the grit is removed at the bottom. There is a scraper. From the grit is scraped at the bottom and taken to a central point, from where it is again separated of the organic material, because the sand also contains a lot of organic material. So you have a rake classifier where it separates the actual sand from the organic matter. The organic matter is returned back into the sewage treatment plant. And after the separation of grit and screenings, it goes into a primary treatment, the primary clarifier. It's essentially, again, a civil tank, an RCC tank that is constructed in a circular configuration. It could be rectangular configuration, but circular is easier because you have the mechanism, what we call as the rake mechanism. It's a mechanical equipment with a motor and a gearbox, and it rotates at the bottom very slowly. It rotates at the bottom because whatever settled sludge is there, it has to be taken into a central well from where there is a pipe for discharge of the sludge. So this sludge from a primary clarifier is very rich in organic matter. It is full of calories. So it goes to a sludge digester where it is anaerobically digested downstream, and you can generate biogas from the anaerobic digester, the sludge. So once your suspended solids are predominantly taken off from the water, the next step is to remove the organics, that is the BOD and COD. And as I told you, there's a typical aeration tank. These are again all RCC tanks, which contain the wastewater or the domestic wastewater. And you have the aeration system where you have a blower along with fine bubble diffusers. The fine bubble diffusers are given because you need to have the efficiency of the blower to reduce the power consumption. And just to give an idea, any sewage treatment plant, the maximum cost of treatment goes for the oxygenation, that is the air blower. You have to have massive air blowers to supply the amount of air that is required for the bacteria to oxidize the BOD and COD organic materials and treat the water and reduce the BOD and COD in the treated water outlet. And hence the maximum, almost 60% of the energy used in the sewage treatment plant is only going for providing air for the aeration system. So once the aeration tank performs, the microorganisms perform the duty of removing the dissolved organics, it is taken further into a settling tank where the sludge is settled and the clear water comes out of the clarifier, which is predominant. It is more or less very clear except for some particulate matter again. And so if you see the comparison between drinking water and wastewater treatment, the units for settling tank remains almost the same. And also the downstream filters also remain the same. But here we are actually separating the biomass and not a particulate, the inorganic particulate matter, unlike which is there in the drinking water system. And part of the sludge or the sludge is recycled back. This is called as a return activated sludge because you have to maintain a concentration of around 2,000 to 3,000 milligrams per liter of biomass in the aeration tank. And the excess biomass that is generated, it is wasted. It goes into the sludge digester as shown in the previous slide. So this is a typical cross-section of the anaerobic digester, wherein the sludge that is separated from the primary stage, as well as the biomass that is separated from the secondary, that is the biological system, can be combined and put into a digester. And here again, it's an anaerobic system. There is no oxygen. So in absence of oxygen, the biomass gets into an endogenous phase where it becomes cannibalistic and it eats itself. But what happens in that due course is it goes through a series of biochemical reactions, and finally you have methane as the gas, the biogas, which is predominantly methane, carbon dioxide, and H2S to a certain degree. But essentially it is all methane, which can be used. So the effluent gas is collected at the top because the gas will go up, and the gas can be taken into a gas holder from where it can be reused back into either you can use it for cooking, or the gas can be used to generate electricity through a dual fuel engine. So a lot of plants today are going in for biogas recovery from the waste, because ultimately every wastewater treatment is full of energy. It is full of energy, and there is a lot of organics present in the wastewater. And what happens to the digested sludge? The digested sludge is further dewatered. All the water component is removed, and you see to it that you have maximum solids into it so that the volume of the waste reduces. So there's a cost attached to transportation of the sludge also. Then it is given hydrothermal treatment, wherein you can convert the sludge, the biosludge, into solid fuel, and which can be used back into the industries like biorefinery. It can go into a lot of other uses like electricity generation or source of heat. And also it can be used as natural fertilizer. a lot of these digested sludge is taken by farmers, local farmers, and used as a fertilizer for their fields. Now, the treatment doesn't end there after the biological system, because if you have to reuse the water, most of the treated water sewage is used back into gardening. It can be used for toilet flushings. It can be used for car washings. It can be used as a cooling tower makeup by the industries. So there are various uses of this treated water. Instead of using the fresh water, you can as well use the sewage that is treated and reuse back into these non-potable applications. And this is what is done predominantly all over the world today, because most of the sewage that is generated, they are trying to reuse as much as possible. So for getting the quality of that water, where the reuse quality needs to be better than the secondary treated water, you go for a tertiary treatment. Again, the tertiary treatment is predominantly filtration. You have sand filters. Then post-filtration, you can chlorinate. You can even chlorinate before it goes into the filters. And then you can use ozone, or you can use UV also as a disinfectant, where your treated water becomes completely pathogen-free. And even if somebody touches it by mistake, it is free from any hazards. Otherwise, if it's untreated, it is a hazard for the health. So similarly, like drinking water, there is an Indian standards which has been formed by the Central Pollution Control Board, where your treated water sewage or treated water in terms of industries also, there are different standards. But treated sewage has to meet certain standards based on the point of discharge. If it is an inland surface water, the concentrations of the components like oil and grease, you have particulate matter, ammonia, nitrogen, etc. are different. If it is public sewers, which means it goes downstream for further treatment, then it is different. You can use it for land irrigation. So land irrigation, the treated water quality is slightly more relaxed, because ultimately it is used up by the soil and the plant. And then for a coastal disposal, again, there is a different standard. So the standards have been very well laid by the Pollution Control Board, depending on the point of discharge, the discharge of the treated water. So can we treat this water to drinking water standards? So that's a big question that everybody has in their mind. Yes, we can treat the sewage, the domestic sewage, to a purer form of drinking water, which will be much purer than what you're currently getting from your source, either groundwater or even your freshwater source. And this is being done in Singapore, where the sewage is treated into drinking water. It is bottled, and it is also given to people who visit their plant. But the only problem is there's a psychological limit. There's a psychological barrier where people do not want to drink. But I can tell you this is purer than most of the drinking water that we receive in our houses. And so they are encouraging people to reuse the sewage back into drinking water. It's absolutely safe, absolutely odorless, tasteless, and very, very pure. So maybe this may be the future. It's going to be, as I told you, water has already started getting traded. Some of the hard facts that we need to know about wastewater treatment plants are that they are highly capex intensive. There's a lot of capex in the sense of instead of providing all this equipment. It is not cheap. It is very expensive. The operation cost is also very high, because as I told you, 60% of the operating cost is only for the biological system, the air blower itself. Then you have the power requirement for the pumping and all other equipment, your agitators, etc. So it's highly OPEX intensive. There are also chemical use, large quantities of chemicals that are used, like your chlorine for disinfection. We have ozone. Ozone is also very expensive. And then there is no resource recovery. So in all conventional wastewater treatment plant, there has been no resource recovery as part of the sewage treatment plant. So if you look at this diagram, it shows that it is highly powered and energy intensive. It uses a lot of chemicals, and the treated water is simply disposed. There's absolutely there was no thought also from the municipal corporation to reuse it. And the sludge was being disposed in some landfill, where it will again go back into the soil. So what is the future? The future has to be a circular economy, the only option that we have for sustenance. We need to recirculate the water. We need to recycle the water. We need to recycle the nutrients that are present in wastewater. We also we need to reuse the energy. That means we need to generate energy from wastewater rather than using energy to treat the wastewater. So there's a lot of paradigm shift in the thought process. There's a lot of work going on, and in the next 5 to 10 years, you will find that most of the sewage treatment plant will become a source of energy generation rather than a source of energy sink. So we are going towards that end. So some of the recent advances, as I told you, a paradigm shift is use less chemicals, generate electricity, and generate byproducts in the form of bioplastics and fertilizers from the sludge. And you can go for a zero liquid discharge where not a drop of water goes out of the premises. It is 100% recirculated and recycled back to non-potable or potable use if people are okay to drink it, and also evaporate the small volume of waste that is generated, because all these recycle plants will require a reverse osmosis plant where there is a portion called as rejects, which is basically you're concentrating all the salts and converting most of the water into a very high purity water through the membranes. But the reject has to be managed. For the reject to be managed, it has to go through an evaporator where you evaporate this small quantity of water. The byproduct of the evaporator is salt. So all your salts, predominantly sodium chloride, will again be recovered back from this wastewater treatment plant. So the entire focus has now shifted to make the wastewater treatment plant not a place where all the resources are being used, but to generate resources and preserve all our valuable resources that are already there.
Sairam sir, we have five
So what are
minutes
the
to
drivers
conclude,
of
sir.
paradigm shift? One is reduce at source by segregated treatment, which also reduces the cost of treatment and the complexity of treatment. Reduction in energy consumption. Basically, as I told you, 60% of the energy is used for aeration. So you have new technologies that are coming in, wherein you have anaerobic and aerobic combination. So anaerobic doesn't require much of energy. In fact, it generates energy. So a lot of thrust is being given to use anaerobic and anaerobic as a combination and reduce the net energy consumption, and also to increase the energy, in fact, to generate the energy. So if you see the reduction, so also reduction of footprint and resource recovery from waste. So these are some of the latest developments that are going on. So just to give you an idea, the organic component is almost 14.7 kilojoules per kg COD of energy. And then you have so much of energy that can, power that can be generated. You can generate as high as 140 gigawatts of power from the wastewater treatment plant. And this is going to be a reality in the future, in the next another 10-15 years. So this is one of the plant where the entire plant is energy positive. It is generating energy and supplying it to the grid, and it is not going consuming any energy. It is generating its own energy and using it in the plant. So there is no energy being taken from the government supply. In fact, the excess energy is being given back to the grid. Thank you. And if you have any questions, you may please ask.
Sairam sir, thank you very much, Dr. Shamraja, for your wonderful presentation, outlining the criticality of water as a resource, and also giving a very detailed presentation about the various protocols and the treatment processes which are employed for the treatment of water and wastewater treatment as well. So I have a few questions in hand. I would like to ask them. So RO water treatment as a tertiary treatment process, it generates a lot of waste in terms of the water resources, because around 40 or 50% of wastewater is generated, which is rich in salts. And also the water pH, the final pH of this water which we drink, that is also is very, very debatable. Like there are some recent news about basic pH levels being better than neutral pH, and also about what about the shelf life of those kind of membranes, and are there any alternative technologies like bioremediation filters using algal filters? Can they be an alternative to the RO treatment processes?
Uh, Actually, there's a lot of lag in the question. So I hope I've understood your question properly. Well, your question one is on the pH, the pH that is permitted for drinking water. Yes, for drinking water, the pH is around 7, I would say, which is what is desirable. It can go up to 7.58 also. It is not very. Uh, so the other thing is regarding the membrane life. The membrane life, if you're talking about a domestic wastewater treatment plant, the membrane life is normally around 3 to 4 years. But again, it depends on how you operate the plant. Depending on the skilled operation, and if it is an automatic operation, and depending on the uh, variations in the wastewater, the RO membrane life can go up to more than 5 to 6 years as well. So that RO is a very expensive proposition. However, at the end of it, when your overall treatment cost comes down per unit volume, the RO membranes cost is also coming down because of the scale of operation today. But yes, not every treated water quality requires an RO. You can use ultrafiltration also. After ultrafiltration, you can even use a treated water. RO is essentially only for removal of dissolved solids. It is not for anything else. It's only the salts, and that also is used for monovalent ions, and mostly your chlorine and sodium, chloride and sodium ions. Yes, algal bioremediation can be given to wastewater, but it has not picked up a lot. A lot of research has gone on algal use for treatment of wastewater. But the challenge remains of separation of algae from the water after treatment. Uh, Bacteria settles very fast, so it is not a problem. However, algae doesn't settle so easily, and that is where the challenge lies.
Thank you very much, sir, for your elaborate answers about these questions. So, due to limited time, we will stop this session here. But we would like to interact more about this kind of features, especially regarding this wastewater treatment, because it will be a great asset not only to the university, but it is a very general topic where like a lot of utilization is pending, and I guess like people with your kind of expertise will be very helpful in guiding us in the right direction.
Sure.
Thank you very much,
Please
sir.
do get in touch.
Thank you very much, sir, once again. It's my honest pleasure to introduce Dr. Sai Satish Ramurthy, Assistant Professor, Department of Chemistry, SSS IHL Prashantinilayam campus. Dr. Sai Satish joined the Sri Satya Sai Primary School at Ooty in 1989 and completed his schooling at the Sri Satya Sai Higher Secondary School, Prashantinilayam. He then graduated with a BSc Honours degree in Chemistry from the Brindavan campus in 2001 and then obtained his Masters in Chemistry in 2003 from the Prashantinilayam campus. He received his PhD in Analytical and Environmental Research in 2007 from SSS IHL. His doctoral research focused on the socially relevant problem of fluorosis, endemic in several parts of Andhra Pradesh, especially in the Anantapur district. Following successful completion of his doctoral studies, he served as Research Assistant Professor at the Center for Advanced Sensor Technology CAST and Department of Chemical and Biochemical Engineering at University of Maryland, Baltimore County, USA, and is also associated as a Senior Research Scientist. At CAST, Dr. Sai Satish contributed significantly to the newly emerging plasmonic technologies in developing these next generation sensors based on surface plasmon coupled emission. These promise to lead to ultra sensitive and ultra fast sensors but at low cost. On completion of his 2 years at the University of Maryland, Dr. Sai Satish joined the Department of Chemistry SSS IHL as a DBT Ramalinga Fellow. His present focus at SSS IHL is to develop and validate indigenously designed, low-cost mobile health technologies for the prevention, diagnosis, and subclinical management of heart ailments, perinatal depression, dengue, and hyperbilirubinemia with high accuracy and reproducibility than currently existing systems. He has supervised 4 PhDs and 2 MPhil students. Currently, 5 postdoctoral researchers and 3 PhD scholars are being supervised by him, in addition to 5 project assistants. He also has been the principal investigator for research projects from NGOs and government funding agencies like DST, DBT, ICMR, DRDO, and Tata Education and Development Trust, and has obtained funding to the tune of 5 crores in the last 5 years. Dr. Sai Satish has 80 publications in national and international journals, conference publications, book chapters, and books. He also actively collaborates with internationally reputed institutions that include the FDA at the USA. In the last few months, Dr. Sai Satish and his team of researchers at STAR Lab have developed reliable testing platforms towards detection of COVID-19 antigen in nasopharyngeal swabs or saliva samples, and COVID-19 antibodies in blood or serum or plasma samples. The test times for these rapid kits are less than 10 minutes. The sensitive platforms are being developed at Star Lab SSS IHL will translate into point-of-care technologies with detection limits that are significantly better than currently available testing platforms, and also aid in scaling up of the current screening or testing rates to serve one and all across India, especially in resource-limited settings. With these few words of introduction, I hand over the podium to Dr. Sai Satish.
Om Shri Sai Ram, offering my most humble obeisance at the lotus feet of our beloved Bhagwan, esteemed Vice Chancellor Sir, respected elders, brothers and sisters of the Sai family. Today it's my pleasure and privilege to make this presentation entitled Star Lab Technologies, Start of a Journey from Lab to Industry for Society. So we have our overarching vision as Sarve Jana Sukhino Bhavantu. It is working towards holistic health management using the medical diagnostics as a means to that end. And over the next few minutes, I will be sharing with you the innovations that have come from the Star Lab. So to start off with, it's all about what we look at this point in time is about frugal science, and that has its beginnings way back in 7 to 8 years ago. So the story will be starting 7 to 8 years ago, what happened, and finally how it came to what it is last 3 years and where we are now. So starting off with, we know that if we are talking about fluorescence emission, this requires a fluorimeter, a spectrophotometer that costs around 50 to 55 lakhs Indian rupees. And here we shine light onto a molecule, the molecule emits, and then we study the behavior of that molecule using the fluorescence emission coming off it. So we began to ask the question, how can we do this through frugal means? What if we just picked up a laser pointer that are used in classrooms, or even a low-cost LED light source that is available, use just a prism. And of course, we need a plasmonic substrate. There's a catch there, but we are working towards frugal plasmonic substrates as of now, and have your cell phone. Just use a cell phone and you're able to capture this emission coming off the molecule. And that's what makes this platform called surface plasmon coupled emission. You just need a light source. It could be your laser pointer or a LED, a low-cost LED, a prism that has this plasmonic substrate. You put this together and you use your cell phone to capture this. And we started getting good emission enhancements. The plasmonic substrate we use is, of course, tin silver film on glass. And what it does, it makes this emission unique in the sense that conventionally you have fluorescence going all over, but when you use this plasmonic substrates, it starts giving you directional or anisotropic emission. It is like me speaking in a room without a mic, which is conventional fluorescence. And now if I start speaking in a room with a mic, that is surface plasmon coupled emission, because now all of what the molecule is speaking is getting channelized, is getting captured as an emission, which we are now able to capture on a cell phone. So the images that you see below here are what we have got on any cell phone that you can use. Any of the cell phones that are available today, you can just take it and use it as a detector and capture the emission. And so what we began to do is, now can we play along with the plasmonic substrate that we have to enhance this emission? Can we bump up this emission where we are seeing maybe a few photons that are captured by this detector in conventional fluorescence? If, let's say, we are having 10 photons captured using the surface plasmon coupled emission platform, we could make it 100. And now we were asking the question, what if we can make this 100 into something like 1,000 or 10,000? That is the kind of emission enhancements in fluorescence that we got interested in, because we are trying to find out a needle in a haystack. I will, of course, tell you how that is happening. So we started making simple silver nanoparticles. We thought, okay, how can we reduce the time in making these kind of substrates? We used a bunch of low dimensional carbon materials like graphene, carbon nanotubes, carbon dots, then palladium nanoparticles, coated composites. We started taking composites together. We were playing along with this. And then we found that when we used silver decorated carbon dots, we started getting 1,000-fold enhancements. And this, of course, resulted in a bunch of publications. And we could start showing that, yes, using the same frugal science, using the very same laser pointer, a prism, a low-cost plasmonic substrate that we can engineer in the lab, and a cell phone is good enough for one to start getting this kind of emission enhancements. And this also led to good sensing capabilities. We could start showing that we could detect a bunch of organics, inorganics, biological entities at different detection limits. So whether it was tryptophan at nanomolar level, to LPPLA2 to picomolar level, stannic acid, DNA, dopamine, spermidine, all of these at nanomolar, picomolar, attomolar, femtomolar, and the cortisol we could show at zeptomolar kind of sensitivity. This is literally like finding that close to single molecule detection. And these works subsequently came on as cover page articles in different journals. But there was a very important question that was plaguing all of us as to what's next? What is the next step after a research publication? How do we take the outcome of our research from lab to industry? How can our research serve society? This was something that was burning in our hearts. And that is where we started working towards translational and convergent technologies, those technologies that can meet the needs of the society, that can look at important pain points that are out there that we can really solve and make a difference. And that is what Swami's university has always been about: how to serve society, how do we bring technologies to the doorstep of every individual and serve them better each and every day. And this, we realized that using our sister institutions, these are our true strengths. We have the presence of primary, secondary, and tertiary care hospitals in both urban and rural settings. This was truly our strength. Our sister institutions working day in and day out for taking care of patients at large, whether it is primary, secondary, at all levels, tertiary, all provided completely free of cost. And that is where, at no cost to the patient, and that is where we felt that our uh, whatever science that we have developed can be translated into meaningful technologies that can serve society. So before going on to what are the technologies that we have developed, since this also involves the student population, I just wanted to share with you something important about technology readiness levels. TRLs, as they are called, is a measure of estimating technology maturity of core technologies. This was originally introduced by NASA. The TRL scale is a metric with 9 technology readiness levels for describing the maturity of a technology, right from ideation stage, which is TRL1, the basic technology research that is there, all the way up to TRL9, which shows the commercial readiness, the highest degree of application, where we are saying that, yes, we are ready to launch it out there into the market. That's the kind of TRL transition that we are seeing all the way from TRL1 to TRL9. And this covers proof of concept, prototype development, functional validations from models to real operational environments and clearances of mandatory regulatory barriers, whatever are there, to finally take that prototype across the valley of death to make a meaningful impact in the lives of people. So that is what TRL levels define, and that is what we intended to make of our science and take it as technology. So we have medical diagnostics coming from the STAR lab of the Satyasai Institute of Higher Learning. We have made different, as I mentioned before, novel nano-hybrid nanomaterials for medical diagnostic platforms. We have used them for both point of care and tabletop diagnostics. In the point of care, we have worked towards perinatal depression. There was an earlier question that was asked about mental health, so I'll be speaking a bit of that. Definitely mental health is of concern. We know that the body is the gross form of the mind and the mind is the subtle form of the body. So yes, mental health is of concern and is of great concern, more so today because the pandemic has seen 32% increase in anxiety, stress, depression after the onset of the pandemic. So we have point of care diagnostics working towards perinatal depression, dengue, neonatal jaundice, and on the benchtop side for cardiac health and for monitoring COVID-19. So starting off with perinatal care, this is something that has always been dear to Swami. The mother and child care has always been very close to Swami's heart, and that is where we were interested in perinatal care. Perinatal meaning we are looking at prenatal, that is during pregnancy, and postnatal, that is after delivery of both the mother and the child. So we were working towards having this handheld diagnostic devices for monitoring perinatal depression. And what you see there, the CTRI number, is nothing but the Clinical Trial Registry of India number. We have registered all of these trials as clinical trials after obtaining the institutional ethics committee approval. We have our own institutional ethics committee at the Satyasai Institute of Higher Learning, that is a government recognized body, and these provide us these approvals to go forward with these clinical trials. And as you see here, the TRL level of this project is at 5. And we first wanted to understand the clinical and psychosocial characteristics associated with perinatal depression. And we were interested in the South Indian population. So we were looking at the perinatal care that was happening in our hospital in Brindavan, the Satyasai General Hospital, part of the Satyasai Super Specialty Hospital, and that of the General Hospital in Puttaparthi. And we went about understanding what are the parameters in a rural and urban setting. This involved a collaborative effort of 11 departments from 7 different institutions who came together, and we saw that there is definitely a high incidence of perinatal depression. There's 24% incidence that is happening. And what we are seeing is the incidence is greater in the urban setting than in the rural setting for several reasons. And once we got to know that, yes, definitely this is existing and it is growing in our society. It's growing in India as of today, as a lot of the East aping the West practices happen. We see a greater incidence of this, and that is where we thought, how can we serve or look into this pain point? How can we address this? So as a pregnant woman in her first or second trimester walks up to the doctor, what are the ways and means the doctor can use to assess their the person's mental health, and even as they monitor several other body parameters and so on, whatever biochemical parameters. So we had looked at the longitudinal psychosocial health information, where we collected the Edinburgh postnatal depression scale parameters. We looked at the case report forms where around 80 to 100 different parameters were collected. We had their audio and video consent, of course, collected prior to start of this. And we have looked at greater than 1,700 data points collected from over 350 perinatal women who were enrolled for the study across 5 visits, 2 in the prenatal, that is during the pregnancy, and 3 postnatal, that is after the delivery. We looked at the biomarkers, that is cortisol, estradiol, FT4, TSH. All of these parameters were looked at during the course of the study. And the main thing what we were seeing is what is truly our strength. We are a university that is no doubt has both a rural and an urban presence. So we have a real, in one sense, understanding of what is resource limited settings, because we look at the villages around and see what is the kind of plight that they are going to. So we were trying to answer, how can we come up with those diagnostics that are amenable to low cost settings, low cost resource limited settings. So one of the things is it should be low cost, it should be near real time, and it should be amenable to resource limited settings. That was the kind of things that we had as our guiding principles, even as we went about the frugal science way. So and how can all of this made into a mobile health? So all of this, you will see it is a cell phone based, where all of the data coming off the instrument can go over to a cell phone. So we have these as cell phone based handheld point of care diagnostic devices for rapid, low health, non-invasive monitoring. So we are looking towards saliva, and so rather than go for a pinprick. So how much less painful can you make it for the study subject or the patient in this case, and see that the best is offered to them. So this was, of course, funded by the Tata Trust, the Tata Education and Development Trust. It's been for over a 3-year project that's been happening. And so even as we go along the development of this device, we have collected several other parameters that come along with it, which lead to holistic understanding of what is perinatal health. And we have started with cortisol, but we would like to extend it to serotonin, dopamine, other biomarkers as such, which will lead to integrated understanding of what perinatal health is truly all about. So the next aspect of the study is about the neonatal care. Like I mentioned, mother and child care has always been very dear to us, Bhagwan. And so we have also been working towards handheld mobile-based device for non-invasive monitoring of bilirubin. This is another pain point. So what we found is that generally for children, neonates who are born, there is an accumulation of bilirubin. The hemoglobin is breaking down to bilirubin. And if this bilirubin that is broken down is not pushed out of the system, it tends to accumulate under the skin. And over time, when the concentrations go beyond a permissible limit, they lead to ototoxicity, nephrotoxicity, and it becomes fatal for the neonate. And more so for the dark-skinned babies, this becomes difficult, because usually when you have light-skinned babies, you can make out the yellowness of the skin immediately. The baby can be taken and put under. You have a blue light setting where because of the photo bleaching of bilirubin, it can be, all you just need to do is, once you identify the baby is having hyperbilirubemia or neonatal jaundice, you just need to take the child, place them under blue light phototherapy, as it's called, and ensure that it's bleached. But to do that, it's a very simple thing of taking the baby and keeping it in a phototherapy setting. But to arrive at the decision becomes crucial, and more so for dark-skinned babies. And usually what is done in this case is they do a heel prick method. They look at the heel of the baby. I've seen this on plenty of occasions, and it's very painful because there's a tender skin of the baby, and you'll have to take a lancet, prick the heel of the baby, collect the blood in the capillary, put it into a again, a spectrophotometer that tells you the amount of bilirubin presence, and then you take the decision of whether a phototherapy is needed or not. So we were trying to see how can we make this non-invasive, and that's where we have been working towards transcutaneous bilirubinometer, where you don't need to depend on the total serum bilirubin that is present in the blood, because it correlates well with a measurement across the skin. We can just shine light on the skin of the baby and collect the information, and that is where we use artificial intelligence. It's not that this technology has not been there previously. Yes, this technology has been there, but to once again make it low cost and amenable to resource limited settings. That is the gap that we are trying to bridge with our devices. And by getting in this artificial intelligence into this, we have been able to get good accuracy, which we are building upon, and then make it the results that come of it as close as possible to the total serum bilirubin that you get from the blood. So that way we can ensure at all instances that we are getting the right kind of results for monitoring the baby, non-invasive. Can we make it truly non-invasive without having to prick the baby or the mother or any study subject for that matter, where we cannot avoid such um, interventions where you will have to you will have to draw the blood, but where you can do away with it, we should be trying for that. So we have been always working towards that, and the result that we get in this within 30 seconds we have the results come off the instrument, and we will then be able to decide as to what is the way forward for the management of the baby's healthcare. So we've looked at over 1,500 data points in this case from our hospital settings, from our pediatrics department in the Satyasai General Hospital, and we have been able to get reliable results so far. And this is at a TRL level of 7 out of 9. We have certain MOUs signed in this. We have some papers and some patents that are upcoming in this regard. Going over to other platform that we are developing is it's for catering to dengue, and as we know, it's a communicable disease that we have. So we are looking at a mobile dengue diagnostic technology, once again smartphone based technology, and this is at a TRL level of 4. It's still building up to we are ramping up the efforts in that regard. And once again, the pain point what we are trying to look at is when we have densely populated areas in India, coming of the rain somewhere in the June, July months means we have the mosquito breeding going on. And once that starts, it is just a question of time before dengue sets in. And in the case of pandemic condition that we are currently in, this becomes all the more severe because you have co-infections, you have reinfections of dengue, and when secondary dengue comes in, it can be truly fatal or severe, because as you go from the febrile, critical, and recovery phases, when you have the 3 phases that are involved in dengue, you make this transition. At the critical phase of dengue, it is very critical because that decides whether you go into the recovery or defervescence phase, or it becomes fatal. And there are certain biomarkers that we can monitor in this regard, and we are looking at the NS1, the viral antigen, the IgG, IgM, and some of the cytokines that are coming off it. How can we put all of this together to arrive at a composite endpoint that will help us determine what is the serotype of dengue? What is the kind of infection? Is it primary or secondary? What stage of infection are we in? Are we in febrile, critical, or recovery phase? And all of this, again, at the point of care. So this we had the funding from the DRDO, Defense Research and Development Organization. And this was because we had these dengue outbreaks that were happening even in army camps. So, for Jawan who is out there in a very difficult terrain, can he have this device to monitor his health? We have no doubt showed initially we are showing it for dengue, but this can, as you will see from the presentation, you will see that this is amenable for adaptation to different other analytes and for integrated health as such. So this is again point of care technology. This is the results that you get in this regard is around 40 minutes, because we are looking at a bunch of other parameters and not a single parameter. It is for multiplex detection, and we have enrolled 171 patients and collected different serum and plasma samples from them. And currently the ELISA protocol is being optimized for the related biomarkers and sensor chip optimization. We have once again we have partnered with companies to make this happen, and patents in this regard are also upcoming. So this is a pilot prototype under development and a TRL of 4 out of 9. Going over to cardiac care, this is another, we know that in one sense, India is the diabetes capital of the world, and this leads to several other problems that show up as the effect of diabetes on cardiac health, and several other uh, uh, parameters within the system, within the human body, get affected. But what happens when somebody in, let's say, it's late night and a person gets chest pain? We do not know if it's a false alarm, or is it an acute myocardial infarction, is it heart attack. And that is where, once again, the entire effort, the logistics involved of catering to that particular patient at that point in time becomes difficult. And so we thought, how can we address this pain point? Once again, how can we make this work towards a point of care, or even a tabletop kind of a device, which is again available in a primary health center, in a resource limited setting, in a rural area, in a village. Some elderly gentleman gets chest pain immediately. How can care be provided? Can they be rushed to the primary health center rather than make it all the way to a city which is far away, and we lose a life in that whole logistics effort of reaching that person? So can we make this reach a primary health center that is out there in the village, that can have this device and monitor the health? That's the kind of question that we were asking. And to this, we have a benchtop test prototype that we have developed. And if you see the device that we have developed in comparison with the current technology out there that uses electrochemiluminescence, the cost of the instrument being 40 lakhs from their end, it needs a mini tempo for transport, but more than that, it needs a proper infrastructure to house such a costly equipment that is commercially out there, and it takes 45 minutes and high power consumption. Compared to all of this, if you see our device, you will clearly see that our surface plasmon coupled emission based platform, the cost is low. It can be transported in a suitcase, so we can take that and have it in a primary healthcare setting. It's close to 20 minutes sample to report time, and it can run, it's a standard desktop that can just run on UPS. So any resource limited setting, once again, can use this kind of a platform to start measuring, to look at cardiac troponin T and assess cardiac health as such. So we have, in this case also, we have done a longitudinal collection of blood samples from 350 post myocardial infarction patients, and we have looked at how well their values right at the time of their admission to post the myocardial infarction event, how are they progressing. Those are the things that we have been following up on. And the device that we have has a TRL level of 7 out of 9 in this case, and the final product is under development. This was funded by the Department of Science and Technology, and we had industrial partnerships in this case too. And all of this was achieved because we could develop plasmonic substrates that are truly novel. So one of the substrates that we have recently developed, it can be used as a low-cost signal enhancer for biomedical sensing platforms. And the uniqueness about this nano hybrid is that it is, you can have it ready in room temperature, and it's sunlight mediated synthesis, and all of this actually can be done in 1 minute. And we have filed a provisional for this a provisional patent for this nano hybrid material that we have, because it's an eco-friendly method of synthesis that we have, and tremendous translational applications in the bunch of arena. We have looked at the antibacterial, fungal. We are now working towards even antiviral, looking at how we can take it forward for COVID kind of scenario. So these are entities that form the core of our smart chip, and the material testing for properties, for several other properties, is underway, and the TRL level of this nano composite that we have is 7 out of 9. And coming to the most important thing that's been gratifying to work upon, with the support of our Vice Chancellor, sir, our administration, is this COVID care. And if you were to ask this question 7 to 8 months, whether we would have been working on this at that point in time, we were just thinking, is there a possibility? But it was the full support that our Vice Chancellor, sir, offered to get this project up and rolling, that we have this at what stage it is today. So I thank the administration for this support that's been given at every point of all the projects, and more so this project on COVID care, which is on dual rapid test kits. So what we have here is we look at the gold standard, which is the real-time PCR, and that is of course the perfect thing. You get reliable results. There are no false positives, false negatives, sense high sensitivity, high specificity, all that is there. But are they amenable to resource limited settings? What is the kind of cost? Yes, these days we are seeing the cost coming down significantly, but once again you need the sample to go from a primary health center to a central facility. What's the kind of load that we are having at that facility? All those questions come into place, and that is where we are trying to say, can we make this truly point of care? Can we have this as a bedside tool for a patient, for a person who develops symptoms of being infected with COVID-19? So we do have the rapid kits, but the rapid kits that are conventionally out there have their false positives, false negatives coming in. So you have 70% kind of sensitivity specificity. So our thing was, how can we make that into something like 90 to 95% sensitivity specificity, or even greater, to ensure that we get results as close or as good as an RT-PCR. And towards this, we have partnered with companies to develop antigen detection strips. We have signed MOUs with them and worked actively with them to develop both antigen and antibody detection strips for indigenous detection of this COVID-19. So these rapid kits, as was mentioned earlier, they can detect COVID-19 antigen and the antibody in less than 10 minutes. They require low reagent usage. They are economically viable. And this short test times will aid in scaling up to the current screening and testing rates that are required for India, even as we look wave after wave, second wave, a third wave, as the thing keeps coming in. These kind of diagnostics will help truly monitor and manage healthcare. That's what we are working towards at every point in time. And these are currently in pre-commercialization stage. The test strips are under validation currently, and we have a TRL of 8 or 9 for this technology. The innovation has kits that are housed in two separate plastic cassettes. These are lateral flow assay based, and they have the immunoassays which show for, in the case of a viral antigen, what is the kind of result that you have, whether it's positive, negative, and likewise for the antibodies as well, using these lines that you come here. The C is the control line, and using these other lines marked 1 and 2, you will know whether the person is positive or negative for the antigen or the antibody. So this is the scheme that we have just adapted. So where we look at the infection, what is the recovery, and we can monitor, in fact, how they are placed right from their infection to recovery to long recovery that can happen. So as you can see, once the control lines are removed, you can look at whether they are recently infected, is their recovery in progress, have they recovered, and how they are completely recovered, where the antigen is completely absent, the IgM is completely absent, and only the IgG is present. So we are using these lateral flow assay kits. We'll be clearly able to say whether the person is recently infected, is the recovery is in progress, has he recovered, or they are in a stage of a long recovery, because these days we also see that these long COVID symptoms come up. So these are the innovations that we have from the Star Lab at different stages of the TRL, whether it is perinatal care, neonatal care, the dengue diagnostics, cardiac care, the plasmonic substrates that we have developed, and the dual rapid antigen and antibody COVID-19 test kits. And this is the offering that we have from our institute as an offering to our beloved Bhagwan, where every step that we have put forward, starting 7 to 8 years ago to recent 2-3 years ago, or the last 7 months, has been truly gratifying, because we are completely confident that we have Swami with us, and we are doing this for his children, for the society at large. Every of this technology, whether it is point of care, benchtop, all of this is aimed at that integrated health management in a resource limited setting at near real time at a low cost. All of these are what is been always dear to Swami's heart, and that is what we are working towards every day, to make this as our offering to Swami at every point in time. So I thank you all for giving this opportunity to make the presentation, and the people who have made this possible are the researchers who are working day in and day out in Star Lab, whether it is the postdoctoral researchers, the doctoral research scholars, the project assistants, the immense support, as I mentioned earlier, also from our Vice Chancellor, Sir, the administration, our sister institutions, the entire gamut of doctors, the nurses, the project assistants who come in there, the technical staff who offer their support, the funding agencies, whether it was the DST, DRDO, ICMR, the Tata Trust, each or whether we have got generated our own funding through corporate social responsibility that has come in, all of this making the offering that we have possible. So I thank each and every one of the people who have been involved in this effort, who have given their time and made this possible to where we are today. And we hope that with the blessings of Swami, we can take this forward and make it really serve society. Because at the end, the fulfillment of every science is in its technology that is translational, that is convergent, that can serve the man or woman on the street. So I thank you all once again for having given this opportunity. Thank you, Saira.
Thank you, Dr. Sai Satish, for providing such an insightful presentation. I believe, like, as we have corporate social responsibility, I think in a similar line, we should also have something called academic social responsibility, where academic research should be aligned in such a way that it should translate into a beneficial or productive technology, which can help the society, especially the people who are having limited resources. And you have excellently demonstrated it with your research works, which you have showcased in your presentation. I wish and hope that many of the researchers who are upcoming researchers and also who have established themselves as researchers, they should take up inspiration from your works and do similar kinds of works. So with these few words, we end the session here. And
thank you.
Thank you, Sairans.
Om Shri Sai Ram. We are culminating the two-day international symposium on the topic Recent Advances in Chemical Sciences, which is organized by the Department of Chemistry, Sri Sathya Sai Institute of Higher Learning. In consonance with the objectives of the symposium, eminent personalities from academia and industry delivered excellent and relevant talks spreading across broad spectrum of knowledge covering ultra-fast spectroscopy, nanotechnology, artificial intelligence, drug discovery, wastewater treatment, energy storage devices, and so on. Beginning with the inaugural address by the revered Vice Chancellor, SSSIHL, who briefed the audience on various facets of COVID-19 vaccines, the symposium proceeded with the keynote speech delivered by Professor Chandrasekhar. The professor emphasized on the need of systematic approach of synthesis rather than the serendipity approach for the design on single molecule magnets. The novel views expressed by the professor on synthetic strategies for single molecule magnets of lanthanide complexes have a good scope for further research. This was followed by yet another remarkable talk by Professor Matsumi, who spoke on the recent advances made in the field of lithium-ion batteries in the laboratory at JAST, Japan. He elaborated on the BIAN-based binders and additives, polymerized ionic liquid binders, organoboron solid electrolyte, and PBI-based anode electrolyte. Following this, Dr. Srinivas, in his talk, deliberated on how greener approaches are being applied in the synthesis of marketed drugs. Besides, he also highlighted the need for exploration of eutectic solvents and ionic liquids as greener approaches in the synthesis of pharmaceuticals. While delivering the final talk of the afternoon session, Dr. Jitendra Sharma emphasized on the need for integration of chemistry with allied sciences for building innovative medical technologies that will bring down the medical cost. This thought of Dr. Sharma will definitely make India move a step ahead in the direction of Atmanirbhar Bharat. Delivering the first talk during the post-lunch session on the day one of the symposium, Dr. Devapriya Kumar highlighted that the emerging times demand application of artificial intelligence and machine learning tools in every aspect pertaining to drug designing. Energy prediction, de novo designing of molecules with anticipated biological properties, and even for understanding biological phenomena using modeling studies, talk about any area there is a pressing need for application of AI and ML tools. Dr. Venkat Sharda, the last speaker on day one of the symposium, stressed on the need for advanced nanostructured materials for energy storage applications. She further highlighted the popularity that is being gained by lithium sulfur sodium ion batteries. Dr. Sharda opined that the synthesis of porous carbon material for bio-waste and incorporation of sulfur for battery applications have proved to be highly efficient and hence have a tremendous scope for further research. The second day of the symposium began with a talk by Dr. Challa Kumar, who drew our attention to understanding the global challenges relating to the environment, scientific rigor needed to address these challenges, and inequality in research alongside the problems faced by the researchers as three facets to scientific discovery. He mesmerized the audience by sharing his team's research outcome relating to how the chemical technologies helped in early detection of diseases in human body. Subsequently, Dr. Rachna Sachivani introduced audience to the concept of lean, which implies reduction of waste and non-value added additives from the customer's perspective. She spoke on the 8 forms of waste and how process analytical technology helped in tackling and minimizing waste for enhancing productivity. Following this, Dr. Jyotishman Dasgupta, while delivering the last talk of the morning session, outlined the latest trends in organic photovoltaics. He discussed further the mechanism of life trapping in organic photovoltaics. Finally, Dr. Dasgupta emphasized on the need to comprehend the critical charge loss in OPV and tuning its efficiency by understanding the exciton dynamics using time-resolved spectroscopy. Post-lunch session began with Dr. Shyam Raja giving complete picture about water resource management, covering plethora of issues such as water availability, usage, contamination, and water treatment. The penultimate talk in the symposium was delivered by Dr. Kishore. His talk was centered around the current status of drug development, with specific focus on HIV and Alzheimer's disease. He concluded his talk by highlighting the research under progress, as well as further scope for research in the field of oncology. The symposium was concluded with the talk by Dr. Sai Satish, who spoke at length about the unique medical diagnostic techniques developed at the STAR lab using frugal science for health management. He provided an insight into how the research in their laboratory is being translated into technology in the areas of perinatal care, neonatal care, cardiac care, dengue diagnostics, and plasmonics. He further drew our attention to how the laboratory has been successful in the development of dual rapid COVID test kit which is right now in the pre-commercialization stage. There is indeed plenty to reflect upon, and if this in any way helps in enhancing our individual and collective contributions to meet the global challenges, then this international symposium can truly be adjudged a grand success. Thank you. Sairam.
Revered elders, students, brothers and sisters, a loving Sairam to all of you. I, on behalf of the faculty of Department of Chemistry, Sri Sathya Sai Institute of Higher Learning, offer our collective salutations to our dear Lord and Founder Chancellor Bhagwan Sri Sathya Sai Baba. Bhagwan Baba has been and continues to be our inspiration and guiding light in all our endeavors. He is the wind beneath our wings. I invoke his blessings and grace on all the participants of this online symposium. A great man once said, feeling thankfulness and not expressing it is like wrapping a present and not giving it. So I take this opportunity to express our gratitude to all the people who made this event possible. First and foremost, I extend our heartfelt gratitude to our Vice Chancellor, Professor Dr. Karni Sanjeevi, for his motivation and continuous involvement in organizing this virtual symposium. I thank Professor V. Chandrasekhar, Center Director, TIFR, Hyderabad, who spared time from his busy schedule to grace this occasion and deliver the keynote address. I wish to express our gratitude to all the speakers, both from India and abroad, who readily agreed to participate in this symposium on recent advances in chemical sciences and share their expertise and wisdom with our students, research scholars, and faculty. Thank you, Professor Matsumi, Dr. Srinivas, Dr. Challa Kumar, Dr. Jitendra, Dr. Jyotishman, Dr. Deva, Dr. Sharda, Dr. Krishna Kishore, Dr. Shyam, Dr. Rachna, and Dr. Sai Satish for serving our students a feast with such a varied spread of topics. I hope this is just the beginning and we have many more such opportunities to interact with you in the future. I am grateful to our registrar for giving us this opportunity to organize this symposium and their immense support throughout this event. I am thankful to Professor C. N. Sundaresan, Dean of Research and Director, Brindavan Campus, and Professor G. Nageshwar Rao, Head of the Department, Chemistry, for their continuous support and advice, which has greatly helped towards the successful organization of RACS 2021. I sincerely thank the members of the advisory committee for their valuable suggestions. I acknowledge the support received from all the faculty of Anantapur campus, Brindavan campus, and Prashantinilayam campus. A special thank you to Dr. Sunil and Dr. Smaran for their contribution during the scheduling and implementation of this event. I would like to specifically thank the people who have been the backbone of this virtual event, our technical team. We are grateful for the technical support provided to us by Shri Venkat Raju, Ms. Tabassum, Shri Raghuram, and Shri Vamsi, who made the broadcast of this virtual symposium possible. Thank you everyone for making this event a success.
ॐ जय जगदीश हरे स्वामी सत्य साई हरे भक्त जना संरक्षक भक्त जना संरक्षक पति महेश्वरा ॐ जय जगदीश हरे शशिवदना श्रीकरा सर्वा प्राणपते स्वामी सर्वा आश्रित कल्पलतीका आश्रित कल्पलतीका आवद्बान्धवा ॐ जय जगदीश हरे मातपिता गुरुदैवमु मरियन्तयुनीवे स्वामी मरियन्तयुनीवे नाद ब्रह्म जगन्नाथ नाद ब्रह्म जगन्नाथ नागेन्द्राशयना ॐ जय जगदीश हरे ओंकार रूप ओजस्वी ओ साई महादेव जय सद्गुरुदेवा ओम शांति 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 समस्तलोकाः सुखिनो भवन्तु समस्तलोकाः सुखिनो भवन्तु समस्तलोकाः सुखिनो भवन्तु शांति 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 जय बोलो भगवान श्री सत्य साई बाबा जी की जय